Hello, I want to go through the mechanism for the reaction you'll be running in lab. It is a double-cross aldol condensation. Basically, we're going to do an aldol reaction, followed by a dehydration. It's between two different molecules, acetone and benzaldehyde, and that's why we call it crossed. And we're going to do it twice. A normal aldol condensation takes 5 steps, but since we're doing this twice, this will be 10 steps. Hopefully the second aldol condensation will go a little bit faster after we've seen how the first one goes. The first step for the aldol condensation is to take acetone and make it an enolate. The way you make it an enolate is you deprotonate the alpha carbon, and acetone has 2 alpha carbons, and they both have hydrogens. How come we don't start with the benzaldehyde? Because if you look at the alpha carbon of benzaldehyde, there's no hydrogen there. So we cannot make benzaldehyde an enolate. We say that benzaldehyde is not enolizable. Now to remove the hydrogen or the proton to make it an enolate, I'm going to draw all 3 hydrogens off of that alpha carbon and use the base hydroxide. Draw your 3 lone pairs and the negative. You can use any base that's an oxide, like methoxide or ethoxide. I just happen to choose hydroxide. And the other thing is you want to make, or I prefer that you make the oxygen enolate. What do I mean by that? The oxygen enolate is the enolate where the negative charge is on the oxygen, not on the carbon, not on the alpha carbon. Some textbooks, some websites also put the negative charge directly on this carbon here, but the O enolate is the more stable resonance structure for our enolate. Let me label it O enolate. We're going to be making this several times in the mechanism. Okay, we did create water in the step, so let me put water. And now the next step is we're going to attack benzaldehyde. Okay, we're going to attack acetone's partner. You know where it's going to attack. It's going to attack at the carbonyl carbon, and I'm going to mark it with a dot. And so in this case, when we look at the overall reaction, the alpha carbon is going to be connected to the dot. How do we do that? Well, we reform the double bond between the carbon and oxygen. We take this pi bond and use its 2 electrons to make the attachment, and then we kick up the pi bond to that oxygen. What we get is reformation of the carbonyl. The alpha carbon now is connected to the other molecule, the benzaldehyde that we attacked. We did form an O minus, and I'm going to draw the 3 lone pairs again because we're going to use them. And you don't have to draw the H, but I'm going to draw it here. And we have the benzene ring. Probably starting with the next intermediate, I'm going to abbreviate the benzene with pH, phenyl. We'll see that in the next step. Now, is that it? Okay, so that is the how the enolate attacks the aldehyde, in this case benzaldehyde. The next step is to neutralize. Let's make that O minus and OH. We did create water, not in this previous step, but in the first step. So I'm going to draw it next to the arrow, and let's use the green mechanism arrow to protonate the oxygen anion. What we made in this case after the third step is I call it the aldol product. It's not the final product, right? The final product is the aldol condensation. This is just the aldol product, and like I said, we're going to abbreviate the benzene ring as phenyl The phenyl group is the benzene ring when it's a substituent. And I will keep track of my alpha. I will keep track of the dot. Okay. This is the aldol product, right? This is the aldol product. It's not our final product. Our final product is the dehydrated version, or the condensation of this product here. We created OH minus, and we're going to use that to now deprotonate the alpha carbon again. If this hydrogen in the beginning is acidic because of resonance of the enolate, well, definitely these two hydrogens are acidic as well. And so let us draw those two hydrogens. Okay, let me move this out of the way. Okay, because I want to be very clear, this is a step actually that a lot of people get wrong. We want to get rid of the OH, but there's a specific way to do that. We have to reform an enolate. And so we're going to come in. Now, it would be very tempting to push these electrons here and kick out OH. Do not do that, okay? You have to form the enolate first, and the way I would do that is you bring these two electrons here to make a double bond, and you kick up the pi bond again. Form the enolate. Do not kick out the OH right away. And we get this product. It's another enolate. Okay, let me draw the alpha. I'll put it here, and the dot. Okay, we have to go through this intermediate, and I'm going to label it again. It is the O enolate. That's after step 4. Remember how I said that it takes 5 steps for the complete aldol condensation? Well, here's the 5th step. Did we create anything? We created water. Okay, so the 5th step is this. Reform the double bond. Shift this double bond here. And now we kick out the OH. This is called an E1CB. It's a new type of mechanism. You've heard of E1, you've heard of E2. This is E1 conjugate base. It is because, well, it's E1 because the double bond that was made here, we're going to make it here, happens at the same time the OH leaves. So that's typical E1. When the double bond is made, the OH leaves at the same time. It's called E1CB because we didn't do an E1 here, we did an E1 with the conjugate base. So this is, basic, the negative charge, and it's a conjugate base of our aldol. It's a little bit subtle. I don't expect many people to remember that, okay, that it's called E1CB. I do expect the majority of students to know how to draw the mechanism, okay? If you were in Walden's class, you studied this. You studied aldol products and aldol condensation. For my class, you are studying it right now. And here we have our first aldol condensation product. Look what we get. Okay, it looks like we're halfway done. If you take a look at that versus our product, we're halfway done. Now we have to react the other side. So this is again the aldol condensation product. Okay, but we're going to do it twice. That's why we call it a double cross aldol condensation. Okay, we kicked out OH minus. And now I'm going to go a little bit faster because we're going to repeat the same 5 steps. Okay, do you believe me? Then we have 5. What color can I use? Dark green. 1, 2, 3, 4, and 5. Okay, I have space to do the next 5. I'm going to do this fairly quickly. It's the same 5 steps, okay? And I'm going to try to do this without saying too many words. Okay, that's another way to draw benzaldehyde. And let me do all the labeling again. Oh, I didn't plan this out too well. I should have turned this molecule around so this part is closer. I'll do that in the next step. Okay. Let me turn the molecule around. There's the dot. Do you remember what happens next? We have to protonate. We want to get the neutral aldol product. We want to get something like this, right? The aldol product. That happens after the 3rd step. And so now we have 6, 7, 8. Okay. We know what we want to get rid of. We want to get rid of that OH, but we can't get rid of it right away. We have to go through this weird mechanism where you have to make the enolate again. We did create OH minus. And let's go down this way. We're going to form the enolate again. And we're 1 step away, right? I said 10 steps total. Where's the double bond? Here's the double bond. The OH is still there. We're going to kick it out next. We created water. All right, we're 1 step away. Just reform this double bond. Okay. These 3 arrows are the same as these 3 arrows. Do you see that? And then our final product is pretty conjugated. We have a bunch of double bond, single bond, etc. Arrangement. And one last thing. Okay. Let me zoom out a little bit so you see the full mechanism. Let me number the steps to prove to you that this was a double Aldol condensation. We did the condensation twice. We did the first condensation in this reaction here to kick out the OH to make the double bond. And then we did again here to make this double bond. That is the full mechanism. If you read through the whole lab procedure, I mentioned there's going to be a quiz after I give the pre-lab lecture. I will not ask you for the full mechanism, but I could ask you to give me the first 5 steps or the first 3 steps, Or even one of your example problems in the handout was to draw the last 5 steps, right? I started you out from here and asked you to go to the final product. 1, 2, 3, 4, 5. Okay. Practice. Come by my drop-in hours if you want some more hints, or if you just want to see if you could do this on the board or on a piece of paper under timed conditions. It takes practice.